In this video, we're going to look at delta G. And the first delta G we're going to look at is delta G of formation or free energy of formation. And that just says, what is the change in free energy when we make a compound or an element? And we're going to look at this by looking at this table. So, for example, when we make carbon monoxide, what is the free energy change of making that compound? And it is negative 137.2 kilojoules per mole. So that's a favorable free energy. So that's usually a spontaneous reaction. Some things to note about free energy of formation. If a free energy of formation is zero, like it's here in this chart, that means that element is in its pure form. Pure element. That's the form that it's normally found in. For example, we have two different carbons here, carbon graphite and carbon diamond. Carbon graphite is the pure form of carbon because it has a free energy of zero. That's what carbon is most likely going to be in. And that makes sense because we know diamonds are more rare. That's why they're more expensive rather than graphite, which is so cheap we use it to write with. Now, delta G, let's look at some of the relationships of delta G. First, we have to realize that delta G is a state function. That means it does not matter where or what path you take when calculating delta G. All delta G cares about is your initial state and your final state, or your initial value and your final value. That's all you have to look at when calculating delta G. Since this is the case, you can reverse a reaction and you'll get the same value of delta G back out, just with a different sign in front of it. And if you double or triple the amount of starting material in your reaction, then your delta G is doubled or tripled. And so let's take a look at this reversibility and free energy principle. To do that, we're going to have sand that's above gas, and this sand is being held up by the pressure of this gas, and right now they're in balance. And so what happens if you remove like 1 grain of sand? The pressure is going to raise up that platform by a certain amount. And you can put that 1 grain of sand back on, and then the platform will lower by the amount it was raised by. So that's what we mean by a state function, and that is reversible. You can put the sand on, take the sand off, and that platform is going to raise or lower based on whether you're putting sand on or sand off. However, most reactions are not reversible. Most reactions only go one way. That's because during a reaction, you lose a lot of energy to heat, as shown by this light bulb. For the old-fashioned light bulbs, 100 watts of your energy, 95% of that energy were going towards heat. 5% of your energy was being used for light. So in chemical reactions, we lose some of the energy due to heat. Therefore, we don't have enough energy to go back. So a lot of reactions are not reversible. So let's look at delta G for standard and non-standard conditions. Delta G naught is standard conditions. All that means is that people agree the amount of stuff you start with and your temperature and your pressure. So standard conditions are normal states, so that's when that table reads 0 for the delta G of formation at some temperature that you would state. It's usually 25 C, I believe. Pressure of gases are at 1 atmosphere, and the concentration of all your solutions is 1 molar. So if you want to use non-standard conditions, which we really care about, because when you do actual reactions in the real world, you are hardly ever in standard conditions. 99.9% of the time, you will be under non-standard conditions. That just means these 3 conditions aren't met. Therefore, if we want to know the free energy change of our non-standard state, it is delta G, which is our non-standard conditions, equals delta G naught, which is the change in energy of our reaction under our standard conditions, plus RT, R is the gas constant, just number, times T, temperature, multiplied by the natural log of Q. Remember, Q is your reaction quotient. That is your amount of products divided by the amount of reactants and there's no liquids and no solids. If your reaction is at equilibrium, then your delta G is at 0. And if you're at equilibrium and delta G is 0, what you can do is, from the previous reaction, you can just move RT ln of Q over to the other side, and you do that by subtracting RT ln of Q, and you get delta G naught equals minus RT ln of K. Remember, K is the equilibrium concentrations of your products compared to your reactants. Therefore, if you are at equilibrium, Q equals K, and that's why K is in these parentheses. Now, if your delta G is, if your Q is less than 1, the value of delta G naught is positive, and that means that the reaction is spontaneous when going from products to reactants. So this reaction runs in reverse. If K is greater than 1, delta G naught is negative. That means this reaction is spontaneous. It will take the reactants and form products spontaneously. And if K is equal to 1, delta G naught is 0, and the reaction is at equilibrium under your standard conditions. And you might be wondering, or maybe not, but we have to look at why our equilibrium constant has this component of temperature. Well, we have 2 different equations for delta G naught. We have delta G naught equals delta H naught minus T delta S, and delta G naught equals minus RT ln of K. Remember, delta H, enthalpy, heat, delta S, entropy, chaos. We can combine those 2 equations because they're both equal to delta G naught. So I can say delta H naught minus T delta S equals minus RT ln of Q. Now here is a math, just a bunch of math that we got to this state. So you don't really have to worry about how we got to this state. Just realize we did some math manipulation to say that, well, when you combine these 2 equations, you see that the natural log of K equals your change in enthalpy divided by your gas constant multiplied by 1 over T plus your change in entropy or chaos divided by your gas constant. This equation looks like y equals mx plus b. And so you can graph this. ln of K would be your y, 1 over T would be your x. Your slope is delta H over R, and your y-intercept is delta S over R. And that's all for this video, and I will see you in the next video.